Okay, we have part 3 now of 19.3 circle theorems. So what is shown in the diagram is something we have looked at EMAF. This is tangents. It's a tangent to the circle, and T is also a tangent to the circle. Both of them meet at the point T. So what we have here, one of the tangent properties, okay, that we have here that we will learn is that when the two tangents actually meet at the external point, tangents to an external point, we know that BT is equals to AT, and we also know that angle OTA is equals to angle OTB. Alright, so these are the tangent properties we'll use for the next two questions that we will be looking at. Okay, example 11. So in example 11, okay, what we have is two circles, alright, with the centers A and B which touch each other at C. Okay, so they have the point C there. The common tangents PK and MC, alright, meet at point M over here. So that means, right, what they mean is TPK is tangent to both the small circle and the large circle as well. So prove that M is a midpoint of PK. Okay, before you read this, what I call the solution itself, what I'll do here is this. Let me just highlight for you to help you in the understanding here. So if I highlight this green circle, okay, tangents to a point, we have PM, okay, and CM itself. So what we have here is this. Since they are tangents to a point, okay, point M, PM is equals to MC. Alright, so far, that's how we get this solution here. Now, if I just erase this and I look at the big circle now. So if I go and look at the big circle itself, okay, what we have here is the tangents CM and KM, they also meet at the tangent, at the external point M. So this implies that CM and KM are also equal, tangents to an external point. So I can write PM equals to MC and MK equals to MC. Since MC is a common thing, what I can say is that PM is equals to MK. So this is equals to this is equals to this. So therefore, the common one is MC, so therefore PM is equals to MK. And if these two lengths are equal, it means that it bisects the line. So M, okay, is the midpoint of PK itself. Now, if I want to do the next part to prove that AM is perpendicular to MB, alright, what I can do here is this. Let me just erase all of this. First and foremost, what I will do here is in this case, we need to actually draw extra lines. So I draw the line AM, and I will also draw the line BM. Okay, now what we will have here is this. First and foremost, what I know is angle AMC and AMP are equal. Okay, these are tangent properties. So AMC and AMP, these two angles are equal to each other. Similarly, BMC, okay, and BMK are equal because these are tangent properties, because this is both of them are tangent. And similarly for the other circle, these two lines are tangent to each other. Hence, this angle is equal to this angle is equals to this angle itself. So now what I'm going to do here is this. What I will do is I'll add the four angles. 1, 2, 3, and 4. This is a straight line, so therefore angle 1 plus angle 2 plus angle 3 plus angle 4 should add up to 180 degrees, which I will actually show here. Now, what do you know about AMC and AMP? They are AMC, AMP, as I've explained earlier, they're actually equal. So instead of having AMC plus AMP, I can actually rewrite it as AMC plus AMC. That's why I have 2 AMC here. Similarly, BMC and BMK, they are the same angle. So I'll replace BMK with BMC over here. So therefore, I have 2 of angle BMC. Once I have written this out, we have almost proven that AM is perpendicular to MB. How? I just divide by 2, divide by 2, divide by 2. I have AMC plus BMC equals to 90. So if you look, AMC plus BMC is equals to 90 degrees. Over here, this angle here is 90 degrees. Hence, okay, AMB is equals to 90 degrees, which proves that it is perpendicular. AM is actually perpendicular to MB itself. Okay, lastly, part 3, show that TPA and TKB are similar. First and foremost, we have proven, okay, the TPA is 90 degrees. Why? TPA is 90 degrees because this is tangent perpendicular to radius. This is 90. And just a few moments ago, we have actually proven that angle TKB, we also know that by the same property, TKB is also 90 degrees because tangent perpendicular to radius. Also, PTA, all right, is the same angle as KTB. It's a common angle, which I've written over here. Hence, they are similar because of angle-angle similarity. This is a common angle. This angle is 90. This angle is also 90. Hence, they are similar due to AA similarity. Now, if you can, please pause the video and look at try 11. When you're ready to actually look at the answer itself, you can actually unpause the video and I will carry on with try 11. Okay, so try 11 is this. First, they want us to prove that PAB and KBC are isosceles. It's a one-liner, okay? AP is equals to PB, tangent to external point. Similarly, BK is equals to CK, tangent to external point. So I can just write there, PA is PB, KB equals to KC, tangent properties. Hence, both of them are actually isosceles. Now, in part 2, what I want is to find or to show that AB is perpendicular to BC. So what I want to show is that this angle here is 90 degrees. Okay, this one, it takes a bit of explaining, but never mind. Let's do this together. First and foremost, this angle PBA plus PAB, okay, is equals to 180 minus this angle. Okay, basically, all right, if this angle and this angle together, okay, is equals to 180 minus this angle over here, angle sum of triangle, which I wrote here. Okay, now see, PBA and PAB are both the same angle, so because of tangents to external point, therefore what I'm going to do over here is I'll rewrite PAB to be equals to PBA. It's the same angle, so 1 PBA, 2 BBA is equals to 180 minus angle of APB. Similarly, for triangle KBC, angle KCB, KBC, okay, is equals to 180 minus BKC, which I've written over here. So basically, this angle plus this angle is equals to 180 degrees minus angle of BKC, this angle over here. Now, similar idea, what I will say here is this. Notice that KBC and KCB are the same angle because the triangle is isosceles as proven in part 1. So I can actually replace KCB with KBC. So 2 of KBC is 180 degrees minus angle BKC. Now here, so what I'm going to do here is this. Let me just use my highlighter function. So basically what I'm going to do is 2 angle of KBC is this, and 2 angle of PBA is equals to this. So what I can say is this, I just add all of them together. Okay, so now what I do is I will add this line and this line to form this line here. So 2 of angle PBA plus 2 of angle KBC is equals to, okay, let me just do this step by step. So 2 of angle PBA plus 2 of angle KBC is equals to 180 plus 180 is 360, then minus angle APB minus angle of BKC. Now, what I can do here is I can divide everything by 2, divide by 2, divide by 2, divide by 2, divide by 2. But before I do that, let me do some simplification first. So, 2 of angle PBA plus 2 of angle KBC equals to 360. Now, if I factorize negative 1, I got angle APB plus angle BKC. Now, what is so special about this? APB plus BKC is given from above, that is equals to 180 degrees. So I can actually cancel this out and write that this is equals to 180 degrees. Hence, 2 of angle PBA plus 2 of angle KBC is equals to 180 degrees. Now, all that's left to do is divide by 2, divide by 2, divide by 2. What I get is PBA plus angle KBC is 90. So, if this angle plus this angle is equals to 90 degrees, to find angle ABC, what I do is I take 180 degrees minus angle of APB plus angle of KBC, which is actually equals to 180 minus 90, I get 90 degrees. So in the working there, I have written it down. 180 minus 90, my angle of ABC is 90 degrees. So I've proven that it's 90. Now, since this is 90 degrees, what we know from the property is that angles in semicircle is equal to 90 degrees. Therefore, by converse, AC is a diameter. And that's it for part 3 of 19.3.